I've known Eric for a long time, since he was a graduate student at Northwestern. And Eric always impressed me along a couple different attributes. One is intellectual curiosity. It was always very, very evidently there. He's always asking me hard questions and probing stuff. And he's always thinking about stuff that's, even stuff out of the box and innovative in different ways and the like. And it's been kind of fun to watch some of those ideas develop and mature and the like. Well, so it's been my privilege to kind of try to follow his research, and and I'm very pleased to be in an event that gets to recognize him as a distinguished scholar. So let me get started here. I'm going to be talking about what I believe to be useful ways to do diagnostics in dynamic structural models. And I'm going to take this as my laboratory, a climate change model. Now, climate change, we could write dozens of papers on from various different angles. So I'm going to be focusing completely on an uncertainty angle. And I'm putting aside some other important questions like coordinations of policies and about even kind of the heterogeneous impacts of climate change across different regions and the like. These are all very, 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 very important topics. But I'm going to focus on a stylized model in order to get at some what I think are very important uncertainty trade-offs, and to try to and to exposit some outcomes that at least some might find to be surprising. I have collaborators Mike Barnett and Buzz Brock. So as economists, we always like to think of trade-offs. And for me, uncertainty, there's two trade-offs of interest, and then they show up in model building. One is, when I use a model, how much weight do I put on best guesses, and how much weight do I put on potentially bad outcomes? If I load everything on best guesses, then maybe a non-trivial probability something bad happens, and that's it. On the other hand, if I go only for bad outcomes, I might not get up in the morning and just quit. I mean, there's an intermediate ground there that I think is very, very important when thinking about policy and more generally, even private sector decision making. The other one, and this shows up in a lot of the dialogue about climate change: do we act now or do we wait until we learn more? So one argument is that, oh, well, once you put uncertainty on the table, yes, we agree there's uncertainty, we should just wait until we figure stuff out. Okay, so I'm going to want to put a model that's rich enough to allow me to address that trade-off as well. In order they can think about this acting now versus waiting until we learn more. Now, the climate change literature has uncertainty treated in fairly modest ways, and we're trying to push that frontier. But I will be using a very stylized model to get us there. Okay. So the underlying model, which I'm going to describe, and then I'm going to try to do kind of an interpretation of it in the latter part of my talk. There's limits to our understanding of potential economic impact of climate change. I think lots of people can agree on that. We know lots of evidence about a human impact on the environment, but the quantitative magnitudes, the time horizon which it plays out, and the like are uncertain. So what we want to do, what we do is we load in 4 different sources of uncertainty, 4 channels of uncertainty. One is productivity. That's the usual kind of macro type, macro finance type uncertainty. I can make an investment today. It has uncertain payoffs because of technological randomness in the future, in terms of or productivity randomness in the future. We're going to address this with a very simple stylized kind of macro model of investment. Okay? Then another one is geosciences. Okay, a CO2 emissions today will impact the future climate. That's uncertain. We're actually loading inputs by looking across a whole bunch of different climate models and kind of what they tell us. The third one is economics. If I do climate change in the future, it's going to alter economic opportunities and social well-being. We're basically pushing the world potentially into places that it hasn't really experienced, and how much economies will get modified, adapt, other stuff. It's not obvious exactly how much it translates, say, changes in the climate into changes in economic opportunities. And that piece of uncertainty has been discussed a fair bit in the literature. Finally, one that we're adding here that is not well studied yet, it's important to our analysis, is technology, research and development. Investments in research and development today may eventually lead to economically viable technology that gets us out of this climate change problem. Okay, now the technology, the R&D I'm talking about here is not going to be the type that sometimes show up as in lots of literature that kind of evolves really smoothly and I make kind of gradual progress on stuff like that. Right? And, that could be present as I'm trying to make renewable energy as more and more economically viable. We're going to talk about big event stuff. So stylized examples would be nuclear fusion. Some people argue that, well, nuclear fusion, it's not yet economically viable. If we make progress, if we make enough progress down the road, then at some point in time, it can allow us to have fully clean energy sources and not rely on fossil fuel emissions. Another one, say, a stylized example might be solar geoengineering. I've got one of my colleagues at Chicago was big onto this, and this is where you kind of put different aerosols into the atmosphere in order to induce some form of cooling. And this is there's discussions about that as a possible way forward, and the like. So these are technological advances that could have very big impacts on things, but they're arguably uncertain in terms of when they'll pay off and kind of over what time horizon. I was recently at a conference last week where the expert in nuclear fusion, Steve Colley from Princeton, I was talking to him privately, and he told me the following: that it used to be people would think that nuclear fusion as a replacement energy sources always 3 decades away. But it'll always be 3 decades away. He said, well, now we've made progress because now we think it's always only just 1 decade away. But anyway, it remains uncertain of what horizon is going to pay out. So I want to be thinking about that type of technological change. Okay, so that's going forward. I want to confront uncertainty, and there's a term rational is loaded here. There's different axiomatic treatments of decision making under uncertainty. Each of them would have their own statement of what it means to be rational. There's different axiomatic systems. I don't want they can lead you to approaching it in different ways. So I prefer to use the term prudent here. I think it's kind of loaded in the context of uncertainty. I want to take a broad perspective on this uncertainty. I want to do kind of risk. We build models, we stick in shocks, we give known distributions. I want to think about that as the equivalent of coin flips and dice rolling. We know probabilities but not outcomes. Then as statisticians, of course, there may be multiple models. Models may have unknown parameters, but there's and the like. We could imagine situations in which, well, let the data speak. It solves the ambiguity problem. But this climate change problem, the climate change thing is, I think it's these subjective inputs. The prior uncertainty here becomes a big deal. The third one is these models write down. They're highly stylized for all components of them. So in some very little sense, they're wrong. You think about this as a form of likelihood uncertainty, and how can we use kind of flawed models, models we know they're simplified abstractions in intelligent ways. So we want to approach these. Now, today's talk is going to be primarily the third channel. Although the third channel actually, or the third approach, the third one actually looks a little bit, components of it are going to look a lot like the second one. So there's a kind of, the second and third are kind of blurred in some of the stuff we're doing. So let me just describe the decision problem without getting into lots of details. We're going to be solving a so-called recursive max-min game. I'm going to invent this adversarial agent such that whenever I consider any hypothetical course of action, this agent's going to look at where the uncertainties are over probability assignments and figure out which ones what's most adverse for that course of action. Of course, what's most adverse for that is going to differ for each course of action, and so I have to do this for every hypothetical choice. Okay. So I'm going to maximize over the decision processes. This is going to be investment in R&D, emissions reductions, and the like. but there's going to be this minimization going on, and the minimization is going to produce a probability distribution. It's going to be, we're going to take a baseline probability distribution and produce an adjusted one. It's going to play mathematically roles like when we do risk neutral probabilities. These are conceptually different, but mathematically we're kind of going to use them in very similar ways, and then going to play a big role in terms of valuation. Now, as external analysts, we don't really know how much, it's not my job to tell society how averse they ought to be to uncertainty. So at the end of the day, our research does kind of a sensitivity analysis over the different types of uncertainty aversion captured by certain penalization parameters. But the important thing for valuation, and that's going to be a central part of what I want to talk about today, is that it's going to be represented in terms of these minimizing probabilities. So the solution to the min part, part of this is used in terms of computing valuations. Okay. Now, we want to use this uncertainty. We end up using this uncertainty framework in the following way. I said we've got these 4 channels. I sketched them all out. Productivity, geoscientific, economic damages, technology. We're going to activate all 4 simultaneously with our uncertainty inputs, and then we're going to activate one at a time. Okay? Then we're going to see how much to get out of which of these sources get you the closest to the so-called prudent course of action. Do you need multiple ones simultaneously, or does one kind of dominate? Now, in the way that we set up our model currently with our uncertainty inputs, what happens is, so we'll solve this under these, under these different configurations. What happened in our current configuration was number 4, technology uncertainty. The uncertain payoff of this research and development, it really kind of took over the uncertainty calculations. Had we left it out, I suspect damages would have been kind of the dominant source. But anyway, this technology comes uncertainty plays a big role. Okay, and in fact, it plays a role in the following. You're uncertain about the prospects of this technology, but it's going to show in our calculations. We find that uncertainty leads you to want to do more investment in this R&D rather than less. So when you present this to standard asset pricing, people sometimes will say, "This, suppose I have a portfolio with all multiple investments, and I start making one more uncertain, and I'm going to push away towards the other ones." Well, that's not the right analogy here, and I'm going to have to kind of sketch out why, because that's not what happens, and that's not what happens in our calculations. Okay. So I'm going to go through this model somewhat quickly. It's a highly stylized model because I want to get to the kind of the interpretations on which we're getting, where asset pricing will play a key role. So we have these diffusion dynamics. Think of Y as the so-called temperature anomaly. We omit we omit carbon in the atmosphere. Roughly speaking, it has a permanent effect. That effect as measured on different models are different, and that's what this theta sub m is all about. And then we include a stochastic component to this. So this is kind of Brownian uncertainty plus uncertainty over which is the right model. Okay? So here I just tabulated what you can get out of a histogram from 144 different models to say, this is non-trivial uncertainty. This is the geoscientific side. If I look at that sensitivity parameter, it can go from pulse experiments to these different large-scale climate models. It can range all the way from 1 to something in excess of 2.5 in terms of these multiplier effects. So there's non-trivial uncertainty here. Now, this is a histogram tabulating stuff across models. To make these probabilities, you'd have to say all models are equally likely. Well, you may not be confident that that's the right way to go, but that'd be one probability assignment. But we want to entertain other ones as well. Now we're going to, for damages, I'm going to have a stochastic model of damages. What I want to get at this fact is you're going to figure stuff is down the road, you're going to know more things. Okay, I'm going to do this in a highly stylized way. Somewhere between a temperature anomaly of 1.5 and 2, what's going to happen is there's going to be this damage curve function. You're going to figure out the tail curvature from it. Right now, you're unsure as you kind of push into kind of warmer and warmer temperature, how much damages are going to be done. But once you trigger this event, you're going to figure it out. So this is just an informational event. So down the road, you're going to know more about damages that than you know now. And that's what, and the idea is that once we start to observe, once climate change becomes more evident to society, it'll be all the easier to act in some sense. Okay. But there's going to be, but ex ante, there's uncertainty about how much damages there is. Okay? It's just going to eventually get revealed. Okay? So here's like pictorially, roughly what we're getting. Think of these as proportional reductions in overall output in the economy. If the event gets realized that temperature anomaly 1.5, which we're very close to, then you get these kind of these red, the red shaded curves are showing you the possibilities, with the red solid line being the average. And the blue one is what happens if it delays until 2. The curvatures eventually kick in, but they kick in at higher temperatures, at higher temperature anomalies. Okay? And somewhere, and where it gets triggered between 1.5 and 2 is going to depend on how much we warmed. Yeah, there's the intensity that's going to depend on the actual temperature anomaly. So as we get closer and closer to 2, we're going to make sure that that there's probability 1, you've basically jumped. Okay? Now, the capital side is kind of boring. It's kind of the simplified version of a macro model. It's going to be an AK model with adjustment costs. There's really nothing, but there will be some Brownian uncertainty attached to it. And that's one of the, and then you take that output, that capital, and then you produce output, and from that output, then you get consumption or investment. And investment can be in the capital stock or in the stock of knowledge. Okay? So this J is going to be kind of a stock of knowledge, which is evolving stochastically as well. But you're going to affect that evolution by making investments, and that's what IT of J is. Okay, and so part of the choice here is how much you want to invest in this this R&D. Okay? Now here's the output constraint. Here we're following Nordhaus, except we don't like some of his parameter configurations. This is like a version of Nordhaus's DICE model, written in a somewhat different way as a production function. And then what's going to happen here is that you have, the way this technology works is you kind of, for large enough inputs, you have basically fixed proportions, and then below that, there's curvature. Now, and at some point in time, you're not going to need the dirty energy at all, and so at that point in time, you escape things, and we'll just get rid of this need for fossil fuels, and you'll get rid of this negative term, which is showing up here. Okay, so as I indicated, our initial research showed that this unknown timing of successive R&D is the most prudent contributor to do this. Now, to make this R&D have any chance, you're going to have to still reduce emissions. You need to reduce emissions today to make the R&D have a bigger and bigger chance to help you out of very severe damages. Now, this uncertainty leads you to do more green R&D, not less. So even though you're cranking up the uncertainty about R&D, you're going to actually want to do more. That's what we'll have to talk about. And you're still going to want to do this emissions reduction. It just so happens the emission reductions coming out of our calculations are not as sensitive to the uncertainty component. But that's still important, because that gives you more time for this. That gives more time for this technology to be developed. Okay. Now, there's going to be competing forces in this investment, and which I want to study. One is uncertainty. There's this uncertainty adjusted distribution. That's going to make you more pessimistic, right? Because you're going to be more uncertainty is going to lead you to, by solving this minimization problem, you're going to explore possibilities of delayed timing in the R&D success. That would seem to push against this notion of trying to be more active. But there's a countervailing force, and that we want to characterize here, and that is the value of the technological success is going to be higher. So, and that's going to work against it. And in truth, this model would have not non-monotone implications, but over a range that interests us, there's this increase, a non-trivial increase in the R&D investment. So to gain a better understanding, I'm going to do the following. There are these key components in these calculations. People talk about this in the climate change literature, the so-called social cost of carbon. For us, it's going to be the social cost of climate change. And there's going to be a social value of research and development. Both of these, we're going to see how we can represent these as asset prices. Okay? And this is where asset pricing is going to come into play. Now the first order conditions for emissions, the first order conditions for R&D are going to look at these guys. And these guys in the model then become these partial derivatives of value functions with respect to these different states. Okay? So I'm going to do what I think of as stochastic impulse response analysis. Okay? What I'm going to imagine is I'm going to take a stochastic system. Our system's nonlinear stochastic. Okay? And I'm going to do a perturbation. I'm going to imagine, suppose I change the state at some initial date a little bit. Okay? And I need to trace out the implications of that. Because of the nonlinearity in this model, that's going to have a stochastic response. So if it this will be a kind of a stochastic impulse response that shows up in order to measure this marginal change. Okay? And you can kind of characterize what that is. That's what I want to do here, just kind of go through what that looks like. Formally, what I'm going to do is I'm going to introduce a process that has the same dimension as the number of states. Okay? So it's going to be one of these is connected to each of the states. The dynamics in the X, though, the dynamics in the state are going to induce some important cross dynamics in these M's. Okay? Now I can initialize this M at one of the coordinate vectors. Whichever coordinate vector I pick, that corresponds to the state which we're perturbing. Okay? Now it's known in this it's known in the stochastic calculus literature that kind of the way that you can do this, the first variational process is kind of what it's called, is M has a drift, and the drift looks just like this. I differentiate mu, each mu with respect to X, and I dot it in with this vector M. And the coefficient of the Brownian increment has the same type of form to it. I differentiate the exposure equation by equation, and then I dot it in with this M vector. And that then I stack all those things together, and that tells me how the M process evolves simultaneously with the X process. So the X process kind of evolves by itself, of course, but then this M feeds back on the X process, and the dynamics will look like this, and we're just going to stack them all together. Okay, what does that do with linear VAR analysis? Well, suppose I let the mu be linear and it should be linear in the state. Then the partial mu with respect to X is just going to be constant. Suppose I have no heteroscedasticity, no stochastic volatility. Then that partial sigma I with respect to X is going to be 0. In that set of circumstances, the M's are deterministic, and they're just going to reproduce counterparts to impulse response functions here. Okay? Now, impulse response functions are typically to shocks and not to changing states, but you can capture those by just changing that initial the way you set the initial M, and you can capture the so-called stochastic responses. There's a formal stochastic calculus literature called Malinbaum differentiation. It's used in option pricing theory. It's tied to this. I'm not going to get into the subtleties of that, but basically, the mathematics that interests me is this M evolution. And this is kind of counterpart to VAR analysis for nonlinear stochastic models. Okay. Next, let me just start. I'm going to use the kind of the tool that we often use in continuous time, writing down a so-called generator. I'm going to look at the local Markov evolution as it applies to conditional expectations of different functions. Ito's formula basically gives us the usual calculation here. There's nothing new there. Now, I can now construct a corresponding generator using those formulas for the joint X and M process. I just go ahead and do fill out how the M evolves as a function of X as well, and then I've got the kind of generator for the composite process. Okay. Now, what I want to do is I want to start off of an equation. This equation is going to be discounted expected utility, basically. Think of U as the instantaneous utility function, V as the so-called value function, the discounted expected utilities, and then A is just the generator. So the discount expected value is kind of known to solve this Feynman-Kak equation, and which is just given here. So this is like take a Hamilton-Jacobi-Bellman equation system, plug in the optimal controls. That's going to be a Feynman-Kak equation, and then you can and it's going to satisfy this. Okay. Now, what I want to do then is get the partial derivatives and represent their solutions as asset prices. Okay. I can differentiate that Feynman-Kak equation. I can differentiate through it. Okay. If I do that, I'm gonna have a different equation for every different state variable. So I'd have a system of equations then. Instead of a single equation, I would now have a system of equations. And I could solve those equations all simultaneously. I could do that. To get something revealing for me, I'm going to do the following, though. It's going to look like a trick, but it's going to have big payoffs. I'm going to take a realization of that big M process, and I'm going to dot it in with this so-called derivative of the Feynman-Cach equations, the vector of them. So that's going to reduce it to a single equation. Once I do that operation, I get a single Feynman-Cach equation. Okay. But now it's a Feynman-Cach equation in terms of this dot product between partial u, partial x, and m. And so you solve that forward, you'll get the equation at the bottom. And this should, look, there should be kind of, this is a very intuitive equation. Think of what you're doing the discounted value of the following. I'm going to differentiate u with respect to x at date t. That's what the u f x at xt is. Then I need to bring that back to the perturbations occurring at date 0. This is where the stochastic process MT comes into play. That's how to get me back to date 0. And then for different choices of that initialization M0, then I can get all the partial derivatives of the value function represented now as an asset price. It's an asset price with a kind of payoff as this partial u, partial x, and stochastic discounting given by this M process, the stochastic impulse responses. So that's the initial asset pricing. That's the initial asset pricing formula. So far, this is not enough for me because there's no jumps here. This is a straight diffusion case. Okay, but this so it's a kind of an intuitive outcome. I've not seen this anywhere in the kind of control theory literature. I've talked to experts and they haven't literally seen this, but in some sense, it's not a terribly surprising formula if you think about the intuition behind it. Okay. So this I basically talked through. We've got this marginal utility contribution, the partial u, partial x, and then you've got the stochastic impulse response. Okay. So when people talk about the social cost of carbon as an asset price, then this is one way to think about it. Now, if you look at how people do that calculation outside of models, like in the climate lab, in principle, they ought to be doing something like this. Instead, they're kind of ignoring a lot of the coupling, the interactions of states, and plugging in various different things in ways that I don't find fully coherent. But in principle, one doesn't have to take the solution to a control problem. You could take a suboptimal dynamic evolution and do the same calculation. And a lot of the social cost of carbon calculations is not about Pigouvian tax policy. It's about figuring out what the impact of marginal changes are in terms of emissions. So anyway, that's a side comment. Now I want to add in jumps. Right? This is going to be really because these jumps are important. The case of damages are this informational events. In case of technology, it's this discovery. So I could analyze this a problem with a whole bunch of repeated jumps and try to do some type of counterpart to what we did for the Brownian piece of it. I'm going to do something else, and I think it's appropriate for this problem. These are big jumps, and there's only two possible jumps one can take. You can take a damage jump or a technology jump. The damage jump, of course, could jump to a bunch of different curves. So I'm going to analyze this problem from a pre-jump perspective before any jumps have taken place. Okay? To do this, then I have to introduce these continuation values. So what I'm going to do is I'm going to load up of all different types of jumps I could have. So in our case, we have one technology jump, and we have 20 different damage curves. So we have 20, an additional 20 different jumps depending upon the different damage realizations. Those are going to be inputs into this calculation. So we're kind of doing backward induction over these jumps in some sense. We're going to have to start at a point which all the jumps have been realized, then only one jump has been realized, and then work our way backward to this problem. Okay. And so now what's going to happen here is that now I'm going to go through and do that differentiation through the so-called Feynman-Cach equation. I'm going to get some new terms. 3 of them. Okay. The first one, I'm going to get, so these J sub L's are the different intensities. There's like, big L different types. We've got, the first one takes that intensity, and the intensity sum, and then looks at the partial derivative of the value function with respect to x. So that's one of the derivatives that shows up. Another one is the difference. Suppose I'm going to differentiate the intensity with respect to x, all L of them, and then I'm going to ask what the consequences. Suppose I jump at that date is. So if I jump at that point in time, I'm going to be moving from the current value function v to a new value continuation value function vj of x, and that's going to be a discrete movement in things. Now, for us, it's going to contribute a so-called flow term to our calculations, just like the partial u partial x does. And there's going to be a third term, and that's going to have to involve differentiating this v sub L with respect to v sub L with respect to x. I know it's a typo. This v super j is supposed to be an L there, but anyway, there's a third term here. It looks just like the first term, but I'm differentiating them. Why? I'm solving endogenously for partial v partial x. The continuation values are imposed under this problem externally. So it's just we need to treat that differently. So these are so it jumps. I have to add these terms in there. Now the first term introduces a discount rate that's state dependent, and so it's, instead of delta now, the discount rate is delta plus the sum of these intensities. This has a kind of obvious interpretation here that this is adjusting for the fact that a jump might take place. So I'm doing those expectations, originally no jumps, and then this is then going to add in the jump probabilities. And that's what this from the intensities. But then in addition to this partial u partial x, I now have two different flow contributions, and the second one is the one that really is going to interest us. That's going to be, say, I'm going to have a marginal change in the intensity as a function of x, and then I'm going to look at what that does to, then I'm going to look at the consequences of these differences in continuation values. Now, here's where these things can be big because the v sub j, suppose I make a discovery of a new technology. Now I've closed out one source of uncertainty here, and so it's so there can be a rather substantial movements going from these these v super j's, and that's going to be important. The third one I think is probably pretty marginal in our calculations, but it's certainly a third piece that shows up. So now let me go back to this robustness notion. I want to have some form of, I want to put this robustness back on the table. I'm going to focus on model misspecification. Now, it turns out that for this example, there's an equivalent interpretation. If you don't like concerns about model misspecification, I think for climate change and other places we should be, but there's a mathematically equivalent recursive utility adjustment. So if you want, there is a pure risk interpretation of what we're doing. It's just not the one that necessarily interests us very much. Okay. Now here's where I'll borrow from derivatives claims that we're going to produce this uncertainty adjusted probability distribution from that minimization problem. We're going to deduce this worst case probability distribution. We're going to have to do a little bit of adjustments or apply the so-called min-max theorem and the like to get to really where we need to be. But then this is going to give us an uncertainty adjusted probability measure. And that's what shows up in the evaluation calculation. So before I had an expectation, now I'm going to have an expectation using this constructed uncertainty adjusted probability. Now this distribution is for sure going to push the prospects of successful R&D into the more distant future. That alone, that by itself, is going to make investing in R&D less attractive because you're now uncertain. And, in the extreme case, I would just say, why do it at all if I really think it has very little prospects? That's this flow term that contributes just like the partial u partial x does. Okay, and that could dominate. And in our calculations, this term does dominate. This is how much you gain. Along the way, if you happen to discover, you make this marginal change in the state, you're going to make this new discovery. And this new discovery is going to, change a lot. It's going to shift to this new value function, to this new continuation value function. And that's going to be substantial. So it's important that you include that, and that's what kind of offsets this kind of pessimistic view of what technology is. Technology, you may be more pessimistic about technology, but its implication for when it happens becomes all the more important. Now, this impact's not monotone. There's not some general theorem that's going to show us that this is monotone. In fact, we know it's not. So let me just close here. This approach has more general applicability to the study of dynamic models under broad notions of uncertainty. It's part of a broader agenda that my collaborators have to explore uncertainty implications for both private and public sector decision-making. And these uncertainty concerns do not, in this example, imply passivity, just the opposite. You actually tend to be more bold rather than more cautious. And then finally, kind of an asset pricing perspective really comes into play here in kind of a nice way. And so it kind of helps us with the interpretation. With that, I thank you for your patience. And I think, as Torben said, I'm out of time, so I will stop here.